Hey, good morning, chemistry. Well, let's see, what was it, Thursday? We had to postpone some stuff so we could get this reaction rate notes and lab done. So we're on page 14, and the factors that can affect the speed of a reaction are four things that we talked about. There's temperature, and we found out that from our class data that when we had the rock salt in hot water, it took about 400 seconds to dissolve versus over 100 seconds longer for the cold. So heat will make reactions go faster. So first off, temperature, heat, and I guess I better zoom in there for you. Heat increases, I'm just going to use an up arrow, increases the rate of a reaction. I'm abbreviating reaction RXN. We'll get into that in a moment. We're just kind of summarizing what we did. Also, the size of the reactants. For our lab, we were doing crystals. Now, the smaller you make the reactants, there's more surface area for them to react. And so when we did our lab here, we found under crystal size that on average the large crystals took over 700 seconds to dissolve. You were supposed to have 0.5 grams of rock salt in there. And then the small crystals took only 474, about 150 seconds less. So the smaller particles dissolved much quicker than the big ones did. So let's come over here, back to those notes over here. Size of reactants. Small size increases. Make sure I'm not going off the page. Amen. Small size increases the rate of reaction. That's almost always true. Coming back, okay, now we talked about the motion of atoms, stirring, moving them. Well, in ours, let's see here, let me adjust this, move that out of the way. Oops. So we had your your flasks. You were to put about 1 gram of table salt in each one. One of them you were to constantly stir. The other one you were not to stir. And what we found out is the one that we stirred, in about a minute and a half, 91 seconds, on average, it broke down, it dissolved. Over here, it took, 3.5 times longer when it was just sitting there. So mixing, stirring, lets things get reacted quicker. So the motion of atoms, mixing increases the rate of reaction. Oh, sorry, went off the page there. Sorry. Mixing increases the rate of reaction. So, why? Let's draw a reactant here. I'm just going to draw it as a cube. Here, you can draw it as whatever you like. But we've got a reactant over there, and the thing is, when it's hot, that means the kinetic energy is increased, because that's what heat is. It's a measure of kinetic energy, the motion of the molecules. Whoops, sorry, let me fix that. Okay. So we've drew this cube. So what happens is, when the material is hot, the water particles, the solvent, whatever it's in, they are moving really fast. I'm going to draw these particles. I'm going to draw a long arrow here to represent they've got a large kinetic energy. They're moving fast. And when they're moving fast, they have more energy to hit. And when they hit moving faster, they can take a bigger chunk out of the material. And the faster this is moving, the more of these collisions. Hot means increased kinetic energy, which means collisions of the molecules increase, that's collisions. And it makes this thing begin to break down faster. Now, if we have something that's cool, so this was hot. If it's cool, this was our hot example. Oh, I guess I should have color-coded that. Oops, okay. Oh well, sorry. This was hot. Okay, over here, if we have the same size reactant, over here, and this is cool. Okay, the particles are still moving, but they don't have as much energy. They don't have as much kinetic energy. And when they do collide, they take a smaller chunk out. And since it's going slower, there's fewer collisions. This is going faster. These guys come knock out a chunk. Okay, they come back. They're moving fast. They're constantly coming through, taking chunks out. Over here, they're going slower. They're taking smaller chunks out. It takes longer for the particle to come back. So that's what it comes down to. It comes down to the kinetic energy of the solvents, the liquidy parts, the other reactants that are mixing with that. Temperature increases that, makes everything move faster. So over here, lots of collisions. Over here, when it's cool, the kinetic energy is lower and there's few collisions. All right, moving right along. Size of the crystals, the reactants. So I'm going to draw over here. We're going to do a small one. So let's say we've got a cube over here. And we're going to say that, let's say that this cube is 1 centimeter on each side. A cubic centimeter, like this guy right here. I should have drawn it bigger. Oh well. This is 1 cubic centimeter. And then let's say we have a large one that's twice its size, okay? So that would mean we've got 1 square here. I'm trying to draw these the same. Then you've got twice the square, but we also got to go twice this way. Okay, it's twice bigger this way and that way. And now let me draw this out, which means this cube that has twice the length altogether, this cube over here, let's see, it is 2 centimeters by 2 centimeters by, where's my other, oh, right there, 2 centimeters. So let's figure out the volume here. Let's go to this one. What is 1 times 1 times 1? Yes, 1 cubic centimeter. That's how big that one is. Now let's take a look at the volume of this one. What is 2 times 2 times 2? Let's see, 2 times 2 is 4. 4 times 2, 8! Hopefully we got, is that 8? I think it's 8. So we have a volume. Volume equals 1 for this one. Volume equals, oh, please tell me I'm on the screen. Good, I am. Volume equals 8 centimeters cubed. Okay, all right, so that's still not really telling us anything. But this one's bigger, this one's smaller, but there's something that's called the surface to volume ratio. This is really important in science, and it's the reason cells are small cells have a large surface to volume ratio. So let's calculate the surface to volume ratios. So surface to volume. So for the large one over here, the surface area, now look at, on the top we've got 1, 2, 3, 4, that would be cubic centimeters, right? And then we have another 4 over here, so we got 4 times, not times, we got to add them up. So we got 1, 2, 3, 4 cubic centimeters. We got another 4 here. Well, it ends up, we've got 6 sides on this cube. Let's see, 1, 2, 3, 4, 5, 6. Now this cube here happens to be twice as big as this one. So let's see, 4 times 6, 4 times 6 is, I think that's 24. So the surface area is 24 centimeters squared. Okay, the 24 of these little square areas, 4, 8, 12, and so on. Its volume, we calculated, was 8 centimeters cubed. What is 24 divided by 8? Okay, let's see. 8 goes into 24 3 times to the 1 time. So the large one has a surface to volume ratio of 3 to 1. Okay, all right. That's telling us how much surface area there is to its volume, 3 to 1. Okay, let's figure out the surface to volume for this little puny square here. Okay, surface area. Okay, now this is just one cube. Each side is a cubic centimeter, excuse me, a square centimeter. There's 6 of them. So that'll be 6 times 1. The surface to volume, make sure we're still visible there, not going off. Okay, we've got 6 surface areas. 6 centimeters squared divided by its volume, 1 times 1 times 1 is 1 centimeter cubed. What is 6 divided by 1, mathematicians, young chemists? Yeah, it's 6 to 1. What? How could the little tiny little stupid cube have such a huge surface to volume ratio? Well, its surface, there's 6 times its surface area compared to 1 of its volumes. This one has 24 surface areas to its 8 cubic centimeters. So this one turns out 3 to 1, 6 to 1. This one has twice as much surface area compared to this, which means whether it's dissolving fast or slow, when those particles start hitting on the small one, they are going to break it down in a few moments fairly quick. This one, in the same amount of time, it's barely, because it's so huge, it's barely had a chance to dissolve. And that's why our cells in our bodies, even the biggest thing like an elephant or a blue whale, their cells are really tiny because it's really quick and easy for CO2 to leave the cell or oxygen to go in. And even the opposite, for nutrients to go into the cell. It's so small, it doesn't take too much time for those to diffuse in and diffuse out. Here, this is so big, if our cells were even twice as big, we would probably begin to starve or suffocate because it takes so long for the oxygen to get in and then converted. So anyway, because this has such a high surface to volume ratio, there's more surface area to be dissolved. It'll dissolve quicker. Okay, lastly, the motion of atoms, stirring. So here's our cube over here. We're going to get 2 cubes again, the same size. So when you stir it, it's kind of like, in a way, like you're heating it up. You're making the solvents, the chemicals, the water in this case, move faster. And if you make these particles physically move faster, you're increasing the kinetic energy. You're increasing the number of collisions. So stirring makes the atoms move faster. Move faster. Kinetic energy, which is motion, increases. You get increased number of collisions. So the motion, the stirring, is bringing particles in faster. And actually what it's also doing too, if this thing begins to dissolve and you get a thick layer of the stuff, the stirring motion carries away the stuff you've dissolved so that now you've got fresh surface area. Over here, the particles are moving slow because you're not stirring, and it'll eventually break it down. But this one is breaking it down fast because the particles are coming in quick and they're hitting all over the place, and pretty soon you've just torn this to pieces. This one is like, hey, what these guys... Okay, so kinetic energy is low, which means there's less collisions. Okay, let's see. Catalyst. A catalyst increases the reaction, increases rate of reaction. But a catalyst is not part of the reaction. But it's not actually used up in it. Up in the reaction. My best example of a catalyst is a piece of paper. you use some scissors, and you can cut that paper into a whole bunch of little tiny things really quick, and when you're done, the scissors are untouched. And that's what catalysts do. But what catalysts do, we got to draw a graph here. Oh, you're going to love the graph. Uh-oh, I'm slightly unprepared for that. Hopefully, do I have the test review sheet here? Dang it, Richard! Why did I not have it here with me? Okay, is it in this drawer? All right, well, let's see. Dang, shoot, get out your test review papers. Yeah, right now, get out your test review papers. Oh, okay, good. There it is, there it is. Okay, I can settle down, settle down. So we're looking at this graph right here. So what happens is it takes a certain amount of energy to get a reaction going. Okay, so what we're going to do is, let's say you have a reaction. This is energy. And we start right here. You've got energy stored in the molecules of the reaction. And this may be like time right here, okay? This is time. So what will happen is, it takes a certain amount of energy. You're going to strike a match. You've got to add some energy to the reaction. And then once you give it enough energy, then the reaction just starts going. Boom, the reaction goes. So you're starting at mid-energy. You give it a little bit of energy, striking the match, or you're beginning to heat up something. Then at some point, the log catches on fire, and it just starts burning, and now all this energy is being released. Okay? Now, if we use a catalyst, so now if we add a catalyst, what a catalyst does, a catalyst makes this, this is called activation energy. Activation energy. It's the energy to start a reaction. Energy to start the reaction. Okay. So if you can get a catalyst involved, what a catalyst, like those scissors, the catalyst, now I'm going to draw this one. I think on your graph they showed activation energy of a catalyzed reaction. The catalyst says, hey, you don't need as much energy. So what happens is the reaction starts going really quick. Okay, so now it's going, it's giving off the energy, and then eventually these, when the reaction's done, they end up, but it's going quicker. It's taken a little bit of time. There's less activation energy. With no catalyst, high. See, no catalyst. The activation energy is high. With a catalyst, the activation energy is low. And so when we were mixing the hydrogen peroxide last week with manganese dioxide, that black powder, the manganese dioxide lowered this so that almost immediately the reaction began. So catalysts reduce the amount of energy to get the reaction going. At the very end, it's going to release all the energy, but look at here, it's going a little bit faster. This energy is going quicker. So that's what a catalyst does. Okay. Bye. Homework tonight. You need to do the even problems on your test review sheet.